All right, welcome back, everybody. Hope you had a refreshing spring break. We got our garden put in, so we're feeling good about that. We celebrated our daughter's first birthday, feeling good about that. And having to dust off the cobwebs to remember what even we did right before break, even though that was just barely a week and a half ago. So last time we had gotten through 2/3 of this slide deck for chapter 7 on Ampere's law. We talked about magnetization. So maybe you see that in your notes from last time. We discussed Ampere's law as just a special case of thinking about the Biot-Savart law, where you can take the path integral around a closed loop. We talked about just like how you can polarize materials by having an external electric field, you can magnetize materials by having an external magnetic field. And what I skipped through last time and did not give much attention to was atomic magnetic moments. So we kind of left off here and said, yes, they exist. We're going to skip that and come back to it after spring break. So here we are. Atomic magnetic moments basically is how we can have a material such as a bar magnet be magnetized on the macro scale to begin with. It is a fundamental property of what we are. Oh man, that's not showing up at all. It's blocked down there at the bottom. Let me change the font size on the slide really quickly. Text size down and present again. Okay, so you can classically, or at least semi-classically, get what the magnetic moment is for an electron that is orbiting around a nucleus. And we said last semester that angular momentum of a point particle, or a particle itself, the angular momentum is equal to mvr. Maybe you remember that, maybe you don't. And the magnetic moment, we said a couple of weeks ago, was equal to mu times Ia. And with some algebra, and you can see the full derivation in your book with some with conservation of energy and everything else, that the magnetic moment of an electron orbiting about the nucleus there is equal to the electron charge divided by 2m, so its mass, the mass of an electron, times the angular momentum of the electron itself orbiting the nucleus. Now, the amazing thing to me seeing this is when you actually go through a full wave mechanic derivation of this around a hydrogen atom, this still comes out to be true, but this is a semi-classical, this is a classical argument, and you still come out to be the same value. The only problem is when you actually take quantum mechanics into its full package, you have to realize that the angular momentum is quantized, therefore the therefore the magnetic moment is also quantized. But at least as far as this little charged particle that is orbiting here, the electron orbiting the nucleus, there is going to be an associated magnetic moment of the electron orbiting about the nucleus. However, there is an additional, for an electron orbital, it turns out that this comes out to be minus E times h bar. H bar is the reduced Planck constant, is what it's called, or Planck's reduced constant, divided by 2 times the electron mass times L over h bar. And we call this EH bar over 2 times the mass of the electron. We call that the Bohr magneton. And the Bohr magneton is this 5 over 57 times, or 5 over 79, times 10 to the minus 5 eV per Tesla. The Bohr magneton. So just be aware of that. We're going to also talk about here that this is just the moment, or the Bohr magneton is. No, what am I trying to say? The magnetic moment here that we're talking about is just the magnetic moment of the electron orbiting the nucleus. But what we've also found is that electrons by themselves have a magnetic moment just associated with the particle itself. And sometimes you can get that the magnetic moment of orbit can align to the magnetic moment of what we'll call spin, and sometimes it will be anti-parallel, and we can talk about effects of that in higher level classes. But suffice it to say, right now, all we're concerned about is this magnetic moment of orbital momentum is going to be equal to the Bohr magneton times the angular momentum over h bar. We'll come back to this here in just a second. But for spin, it turns out that the magnetic moment of spin is -2 times the Bohr magneton times the spin angular momentum. So the angular momentum associated with, if you imagine the electron being this itty-bitty teeny tiny ball that is on the order of angstrom, well, lower than that, sub-angstrom scale, that is rotating, then the amount of charge as it rotates creates a magnetic moment just of the electron itself spinning. Now, when we leave the classical world and enter the world of quantum mechanics, what becomes the problem with this model here, coming up with where the spin magnetic moment comes from? Does anybody remember? Or know ahead of time? I shouldn't say remember. We haven't talked about it yet. Yeah, up here. Yeah, it's infinitesimally small, right? And so to imagine that this is some charge distribution spread out over finite space that is spinning, sure, that works for us. But then if you shrink that into an infinitesimally small space, then giving it spin, like classical spin, meaning rotation, like I spin a basketball on my finger, right? All of that meaning goes away. And yet, the spin magnetic moment stays the same. I saw the question mark pop up here. The whole idea, or at least on the last slide there was a question mark, the whole idea is presuppose that if you remember, we said maybe Tuesday before spring break, that if you have some sort of current going around a closed loop, or even if you just have a closed loop itself of conductive material, then we said that the magnetic moment of that was equal to N times I times A times, I guess it was just that, NIA, right? And so the idea here is that if you have a moving charged particle that is orbiting in some way, shape, or form, like an electron about a nucleus, well, you could imagine that movement of charge, that could be a change in charge in a given region as a function of time. Movement of charge or change in charge, that's a current. So the idea is any moving charge is going to have an associated magnetic moment. The electron orbiting a nucleus has two. One for its orbit about the nucleus, one for its classical idea of its spin. The reason that this becomes important, I think I flashed these slides up here at the end of class, is because you can start thinking of paramagnetism, diamagnetism, and ferromagnetism in terms of these two values, the orbital magnetic moment for the electron cloud and the individual spin magnetic moments for the objects that are orbiting, for the electrons that are orbiting the nucleus. Ferromagnetism is the easiest one to consider. So we go back to our idea of magnetization. What tends to want to happen is you want to have poles that, or what happens in some sort of material, say a block of iron or something like that, is you have these what are called domains. And the domains are going to have regions where the magnetic moments of each of the individual atoms are pointed in the same direction. And so you imagine if I add up a bunch of magnets, little bitty teeny tiny atomic sized magnets that are all pointed in the same direction, then the north end is going to be pointed in one particular direction in that domain, and the magnetic field lines are going to loop about that preferred direction. And so the idea is in each one of these domains where the magnetic moments tend to align, Adjacent domains tend to have magnetic moments that are pointed in random other directions. And so for a block of iron, if you have that each of the domains have magnetic moments that are pointed in all different directions, the net magnetization of the material is zero, right? They all end up canceling out if I've got all these domains that are pointed in different directions. But if I can stick that material in an external magnetic field, what ends up happening is I can turn those domains, the magnetic moments of each of those individual domains, along the direction of the external magnetic field. So now each of the domains all have a magnetic moment that are, say, pointed to the left of the classroom here. And why are the domains pointed that way? Well, it's because we have more or less physically turned the electron cloud for each individual atom in each of those individual domains to orbit such that they are perpendicular to that direction that I have imposed on them, and now their magnetic moments of orbit are all pointed in the same direction. Then I turn off the external magnetic field, and what's left over is the material stays magnetized. So now I've turned this demagnetized block of iron to have a net magnetic moment, and I've created a bar magnet out of this block of iron, or this iron ingot if you're playing Minecraft or going to watch the Minecraft movie in a couple weeks. William, what's your question? Okay. Oh, okay. Okay, so you've got a bar magnet. How do you demagnetize it? There was actually somebody who came up at the end of class on Thursday before spring break who asked the same question. So we talked about magnetizing something. There are three different ways that come to my mind that come towards demagnetizing something. It turns out that if your external magnetic field was pointed to the left of the classroom to magnetize the material, to turn the domains, you can actually create an external magnetic field pointed in the opposite direction of a given strength, and you end up shaking everything up and demagnetizing the material. Another easy way to do it is if you've got a bar magnet, you drop it. The drop sends a shock wave through the block of iron, and it's going to cause everything to jump because we're going to seek a lower energy state, and the lower energy state is where we can cancel out the magnetic field within the actual block of iron. The other way is you heat the block of iron up. Heating the block of iron up gives it enough energy that the domains can start to shift in other directions. So yeah, if you want to demagnetize a magnet, drop it and hope it doesn't break. But that's a good way to do it.
This may be kind of obvious, but you just, like, on iron
Can you switch the direction of magnetization? Yes. So what happens is let's see here. What am I trying to do? You have your demagnetized block of iron. It looks something like this, right? And I'm going to put it in a net magnetic field that looks something like this. And I'm going to increase the strength of that magnetic field over some function of time, right? And assume that this is embedded in it. Well, what happens is I end up getting a north-south induced, and I get a magnetic field coming out of this that looks like so. It turns out that now if you get rid of these magnetic field, the external magnetic field, you get a magnetic field that still remains here, but it's going to be weaker than when the external field was present. So now you start, let me draw a few extra lines here. You've got your magnetic field. I'm not drawing the full loops of these, but just giving you the idea of what the magnetization is, right? So then you turn the magnetization on in the other direction, right? Or the external magnetic field, B external, is going to look something like this. And as you do so, you're going to end up getting some of these magnetic field lines are going to start going away because you're demagnetizing the material. until you get to this point right here, where now you have completely canceled out the magnetic field in that material. And you could shut everything down and you've got a demagnetized bar. Or you could continue adding this net external magnetic field, and as you do so, you end up switching the poles where this is north and this is south, and you get your magnetic field of your iron, your block of iron is going to do something like this. What happens is, you can see this found in your textbook in those chapters that are talked about. This is B external, and this is, let's say, the magnetization, right, of this object here. You're going to have that your block of iron, your magnetic material, is going to start out with no magnetization. And let's say that the external magnetic field is 0. But then I start cranking up the external magnetic field, and let's call this in the X direction, right? So I'm going to be increasing the magnetic field this way. And it turns out that what happens is you get a very quick jump in the magnetization, and then eventually it levels off. I can keep cranking up the strength of the external magnetic field to 1 Tesla, to 2 Tesla, to 10 Tesla, but my magnetization of I can't magnetize it any further. It hits an asymptote. Well, then you can start cranking down your magnetic field strength again to where you get to this point, and then as I start walking back this way, my magnetic field strength is still to the right, but it's getting weaker and weaker and weaker. You get that it starts dropping off to where now your external magnetic field is 0, but your material is still magnetized. So if you want to demagnetize your material, you have to start walking the magnetization stronger to the left, to where eventually you get that your material is demagnetized. And you could keep going to a stronger and stronger magnetic field to the left, in which case you get the same behavior as before. You hit an asymptote in the opposite direction. And then you could walk the process backwards to where you start decreasing the strength to the left. You demagnetize your material again, you overcompensate, and you start increasing it to the right. And so you get this closed, what's called hysteresis loop of how you can magnetize your material one direction or the other. And so it was asked at the end of class, we've got this tool, we've got this piece of equipment in our machine shop that will demagnetize our tools if they become magnetized. And I don't know exactly how it works, but what I suppose happens is the machine doesn't know what the magnetization of your material is, but it knows if it really pushes it strong this way, it can reach a maximum magnetization, and then if it increases it a little bit in the opposite direction, it can demagnetize the material. I don't know about that. I don't know. I would expect it's like, I don't know. I'm speaking out of turn here, but I'm tempted to say that that's a electrostatic interaction instead of a magnetic interaction, but I don't know. All right. I think that was all the slides we needed to cover. Are there any other questions before we jump? The last one was if you want to click on any of these links later on or however you want to do it. These links give you an idea of how magnetic fields are generated from relativity, how magnetism is related to relativity, where paramagnets come from, and how this all could work potentially for point particles. So if you're interested in those, click on any of those links and they'll get you some understanding. But in the are there any questions before we jump to problems? Yeah, Bill? I can pull the attendance thing back up. It says session check-in was completed, so no, I cannot. I only have it open for 25 minutes, but you can catch me after class. Any other questions? Yeah, up here at the top. Yeah, is that a typo? I couldn't remember. I should have written it down last time I gave this lecture. 5.79, that would make more sense. I was just going to run with it and then check it after class and send an announcement if I was wrong, but you looked it up, it's 5.79 Tesla, EV per Tesla. Okay, thank you. I appreciate the clarification, and I will make a note to fix that after class. Okay, where were we? In figure 2755, one current is 8 amps into the page, the other is 8 amps out of the page, and each curve is a circular path. Find B.dl for each path, assuming that each integral is to be evaluated in the counterclockwise direction. Which path, if any, can be used to find the combined magnetic field of the currents? So first things first, part A of this problem. If we want to know the path integral around C1 of B.dl, what would be the value of that? Well, you could go through and look up and remember that, okay, for a long straight wire, the magnetic field is like 1 over 2, it goes as 1 over 2r, I over 2r, something like that. And you could go through and do the integral in the phi direction and integrate from 0 to 2 pi. But what is the simpler way, if you look back in your notes, to figure out what the value of this is? Yes? Ampere's law. Ampere's law states that for a closed loop integral of B around some contour, B.dl, it's equal to mu naught times how much current is enclosed. So in this case, it's going to be equal to mu naught times 8 amps for C1. And let me ask you this. Would that end up being positive or negative? Well, the current is going into the page. It's an X. And so if I try to grab around that wire, my fingers point in the clockwise direction, but I'm taking the integral in the counterclockwise direction. So this is negative here. So that's minus 4 pi times 10 to the minus 7 times a current of 8 amps. And this ends up being here, let's see. This ends up being what? I just wrote it down as minus 8 mu naught. But if you were to actually multiply this out, that would be 32 pi times 10 to the minus 7. 32 pi times 10 to the minus 7. So that's 3 times 3, that's going to be roughly 9.7 times 10 to the minus 6 Tesla. What do y'all get? What do you get when you take 4 pi times 10 to the minus 7 times 8? What? It would be negative, yes. $10.05, okay. Okay, so that's minus 1.05 times 10 to the minus 5 Tesla. Part B, what is the contour integral around contour 2 of B.dl? What is it in that case? Oh, and it wouldn't be Tesla, right? It would be Tesla meters. Well, what's the value for contour 2? It's 0, yeah. I've got as much current going into the page as I've got coming out of the page within that contour. So in this case, you get 0 Tesla meters for the contour integral around that closed loop. And then around loop 3, C3 of B dot dl, well, I've got the same magnitude current, but now it's coming out of the page, and if I do the contour integral, it's going in the same direction as the magnetic field. So in this case, you get plus 1.05 times 10 to the minus 5 Tesla meters for the contour integral. So which path, if any, can be used to find the combined magnetic field of the currents? Well, it can't be C2 because we break symmetry, right? The actual magnetic field here is going to look, I don't know, quite complicated. It's going to be basically a couple of loops, but they're both going to end up, you're going to get something that looks like this here for the magnetic field. They wouldn't loop over one another, but my contour doesn't follow the direction of the magnetic field lines. So it can't be C2. And C1 and C3 don't follow the magnetic field lines. So the correct answer to part B is none of these can be used individually to find the magnetic field of both. But what could you do instead if you wanted to find the magnetic field at any given location here on the map? If I wanted to know the magnetic field of any given point, I can't use C1, C2, C3 by themselves. What's that? C1 and C3 together. Yeah. The one around each wire you could use. So take, for example, if I wanted to know the magnetic field at this point right here, right? Then what happens is I can take C1. I know that by itself, what the magnetic field for this one is going to be a magnetic field that looks something like this from, let's call it B1. And then I could consider that there's a contour around C3 here that's going to look something like this. And using superposition, you can figure out, adding those two magnetic fields together to figure out what the individual magnetic field is at any given point. But you have to use C1 plus C3 instead of using any one by itself. Just using the principle of superposition. Okay. A long cylindrical shell has an inner radius A and an outer radius B and carries a current I parallel to the central axis. Assume that within the material of the shell, the current density is uniformly distributed. Find an expression for the magnetic field when R is less than A, when R is between the two walls of the shell, and C when R is greater than B. So taking a cross-section here, a cross-section of my wire, this is going to be A, and then I've got outside of that, I've got my wire that's going to be of the outer wall here that is of radius B, and the current I is going to be, in this case, let's just say it's coming out of the page. Like so. So these are all individual bits of the current that are coming out of the page. You get the idea. It's got the chicken pox. So how do we calculate? Well, first off, for a contour, for R less than A, what is going to be the magnetic field inside of that region there? It's 0. I have enclosed 0 amount of the charge at this point, so there is 0 magnetic field inside of that region. Good. Just like what we found when we did closed surfaces with Gauss's law. If there was no charge enclosed, there was no electric field. If there's no current enclosed, there's no magnetic field. No net magnetic field at any given point. So part B, this is the one that's really the kicker here. Part C is actually also easy. Part C, if I look at this being R now, well, the integral of B dot dl around that surface is going to be equal to, we're told the current inside is I, so it's going to be equal to mu naught times I. And so it's up to us to figure out what B dot dl is, or particularly what dl is. And what we said is if we're integrating around this region here, this is dl, then one of the things we said early on when we started talking about Gauss's law is that if, let's say this is the angle phi right here, and this is r, then dl is going to be equal to r d phi. And so we get the integral going of b times r d phi is equal to mu naught I. And we're integrating d phi around a closed loop. You remember that there are 360 degrees in a closed circle, or 2 pi radians. So we're just integrating from 0 to 2 pi radians around that circle. Well, b and r do not depend on phi, so that's equal to b times r times the integral from 0 to 2 pi of d phi. But that just comes out to be d phi, 2 pi, excuse me. So I've got b times 2 pi r is equal to mu naught I, or b is equal to mu naught I over 2 pi r, which is exactly what we found when we were doing the Biot-Savart law around a long straight wire. The problem is, or maybe not the problem, the difficult thing is doing part B here. And why might I say that part B is the most difficult part so far? When I'm looking at R being between A and B. The problem for R being between A and B is that I've only enclosed a small bit of the current. Right? Like if I look at this point right here, to be the radius that I'm integrating over, so call this R now, then I is all of the red dots, but I've only enclosed a fraction of them. I've only enclosed a fraction of the surface, the current. And so this goes back to something that we talked about weeks ago now. We described this current density as being I divided by area. Right? So the current density, since it is uniform, is equal to the total amount of current I divided by pi times b squared minus a squared. Now, how did I immediately jump to the current density is I over pi b squared minus a squared? Where did the pi b squared over minus a squared come from? Yes, William? Yeah, so you consider here, let's say that in an ideal sense, I just had a uniform wire here of radius B, right? And I had all the current coming out of this wire of radius B. This would be a cross-section of the wire. Well, in that case, the area of this circle here is equal to pi times the radius, which is B squared. But just like William said, now I want to cut out a circular radius A from the center here. So A is going to be equal to pi B squared minus what area I cut out, so that's pi A squared. Or if I factor out my amount of pi, so that's pi B squared minus A squared, which is exactly what I've got below. And what we said is we can take, according to Ampere's law, the closed loop integral of B dot dl is equal to mu naught times I, but how much current we've enclosed is going to depend on how far out from the center of the circle we are. So it ends up being mu naught times J, times dA. And we said that for a circle, dA, a differential area here, is going to depend on its radius. dA is equal to, r dr d phi. So now B dot dl comes out to be the exact same thing. There's nothing that's changed about this integral, so it comes out to be B times 2 pi r is equal to mu naught times J, which is I over pi B squared minus A squared, times dA, which is r dr d phi. If you're freaking out seeing integrals right now, I'll tell you the same thing that I told you when we covered Gauss's law. I'm showing you the full treatment here just so you know how to attack these problems if you go into higher level physics. But if you'd like to see a geometrical argument to everything that I'm doing here, your book does these problems from a geometrical standpoint. So feel free to look up in your book how to do these more geometrically speaking. In this case, the integral going from, r goes from 0 to r, and phi would still go from 0 to 2 pi. So if I do the integral over r, I've got on the left-hand side b times 2 pi r is equal to mu naught times the integral going from, what do they teach you in Cal 2? I forget. I've gotten lazy at this point. Do you go outside in or inside out? What? I do the r integral first, right? R integral first. Yeah, so I still got my phi going from 0 to 2 pi. And then I got I times pi b squared minus a squared times r squared over 2 d phi. All of this is constant with respect to d phi, so now I've got b times 2 pi r, is equal to mu naught I over pi b squared minus a squared times r squared over 2 times 2 pi. These factors of 2 pi are going to cancel out. A factor of r cancels a factor of r over here, and I'm left with b is equal to mu naught I times r over 2 pi b squared minus a squared. So what do you note about the difference when we're measuring the magnetic field outside of the wire with increasing radius versus measuring the magnetic field inside the wire with increasing radius? Big R being our radius. What do you notice about the difference here? Yeah, the difference between answer B and answer C. Yes, yes. So in part B, I'm excluding this region right here, which gives me something different. But specifically, qualitatively, tell me the difference between those two answers right there. Within the wire, my magnetic field strength gets bigger as I enclose more current. Again, you remember, just like we did with Gauss's law, my contour is growing as a function of r, but the amount of current that I'm gaining grows as a factor of r squared. And so I end up getting that when I'm inside the wire, my magnetic field strength is increasing with radius. Whereas when I leave the wire, my magnetic field strength decreases the further I get from it. You could see it as something like this. If this was B, and this was, I think I made a mistake. I'll see if somebody can catch it here. If this is R, then, and this is A, and this is B, yeah, I made a mistake. Interesting. Okay, we'll see if we can catch it. What this is saying is part A, the magnetic field strength, actually let's use blue so we know what we're talking about here. The magnetic field strength is 0 when we're inside of A. And then according to this, I jump up like so, and then I get to here, and I start dropping off like so. Now there's a problem, because according to my solution here, I have a discontinuity right here. I've made a mistake. I go from 0 magnetic field strength at radius A if I'm looking at inside that wall, but as soon as I go between the walls of the shell, I jump up to some non-zero magnetic field strength right there. Henry?
When you set up the double integral, if you went the limits of integration on r from 0 to r, but since there's no current in the middle, it should be a to r.
Yes. So my problem was this limit of integration right here shouldn't have been from 0 to r. It should have been, my current was only enclosed from A to my radius r. And so in doing that, you would have ended up getting something slightly different. You would have gotten r squared minus a squared, and you would have picked up here a factor of r in the denominator. But still, r squared divided by r, we still get a linear increase. And so now, what we get is something like this, which is exactly how it should look. The embarrassing thing is I've got my solutions up over on the right-hand side, and I'm pretty sure I made the exact same mistake last semester when I taught this. Alas, you get to going too fast. Okay, let's see here. Last one, and then we'll jump to the slides that I wanted to start with today, but we were further behind than I thought we were. A long tungsten core solenoid carries a current. If the core is removed while the current is held constant, does the magnetic field strength in the region inside the solenoid decrease or increase? And by what percentage does the magnetic field strength in the region outside the solenoid decrease or increase? This is a question about magnetization. And what it requires you to know is that, or remember from last time, that the magnetic field inside the material of a magnetized material is equal to the external magnetic field strength times 1 plus what we called chi sub E. Chi sub M, excuse me. Chi sub M is the magnetic susceptibility of the material. And you say, great, I have no idea what the magnetic susceptibility of tungsten is. And what you have to do is, on an exam, I'd have to give it to you or ask you to solve for it based on other material in the exam. Or, at least in this problem, they're assuming that you look up in the textbook, table 27.1, and you find that for tungsten, chi sub M is equal to 6.8 times 10 to the minus 5, and it is a unitless quantity. And so, in part A, it has the tungsten core in there, in which case you're going to have this magnetic field strength, and chi sub M is, in this case, greater than 0. There are some materials where chi sub M is less than 0, meaning that chi sub M for tungsten is positive. And so, if the core is removed, does the magnetic field strength in the region inside the solenoid decrease or increase? Which one? Yeah, it's going to decrease. The magnetic field, if I have 1 plus something greater than 0, so this is going to be a positive value, so this is a value, that's not what I meant to draw. This right here is a value greater than 1, so B times something greater than 1, B is going to be greater than B external. And when I remove the core, it goes back down. So in this case, yeah, we get that there's going to be a decrease in the magnetic field strength. If this had been some sort of material that had a magnetic susceptibility less than 0, negative value, in that case, when you remove the core, the magnetic field strength would have gotten stronger inside the solenoid. Part B, by what percentage does the magnetic field strength in the region inside the solenoid decrease or increase? Well, as we've said, B is equal to B external times 1 plus chi sub M. And if you want to know the percentage difference, that's the same as taking the fraction of change. So that's just 1 plus chi sub M, or that's equal to 1 plus 6.8 times 10 to the minus 5, or that's equal to what? 1.0000068, which means if you want to know the change, you look at this part right here, and take off 2 zeros. So that means that there is a 0.0068% change in the magnetic field strength, meaning a very, very tiny amount. Like this, you'd have to have a very precise instrument to measure the change here. I'd either have to give you the value of what it is for tungsten, or I'd have you work this backwards and say, oh, you notice this amount of change. So what is the susceptibility? And then, in that case, would it increase or decrease? Mm-hmm. Mm-hmm. Good, good. Okay, we've got just under 30 minutes left. Let's switch gears and at least try to introduce the idea of magnetic flux, and then we will see how far we get from there. I have several nieces and nephews, and they all really like Pokemon. Therefore, my 4-year-old son, who has never really played Pokemon before at all in his life, thinks that Pokemon has got to be the coolest thing in the world. So we're constantly, I'll get home from work today, and the first thing that he'll do is he'll attack me with a hydro pump or a thunderbolt or something like that. And I immediately have to go into Pokemon trainer mode. Oh, yeah. Which one was my favorite? Pokemon Yellow was a lot of fun in my youth. I had Blue, Yellow, Silver, Crystal, Let's Go Pikachu, and Scarlet. Basically I aged out, and then I got to where I wanted casual games again, and so I decided I'm an adult, I'll do what I want, and I started playing it again. Yeah, so I have no idea what happened, like Dynamax and Gigantamax and Mega Evolution, like, that's magic to me, but never played any of, like, if it's not the original game platform mechanics, like Pokemon Blue mechanics, I've never played any, except Pokemon Snap, on the Nintendo 64, not on any of the newer platforms. What's that? Yeah, I did play Scarlet. Oh, the Pokemon Snap is, you mean? Really? Yeah, Scarlet was fun. My problem is I'm a completionist, and there are 450 Pokemon in the Pokédex, and I've just given up at this point. I'm not even trying at this point. I am a little disappointed that Squirtle is beating out Charmander. Charmander's my favorite. Squirtle has the best stats, but Charizard is the coolest final evolution, if you ask me. So I like Charmander. And plus, Charizard's like the real mascot of Pokemon. It's not actually Pikachu. Yeah, he's not even Dragon type. Unless you Mega Evolve him and do a Mega X evolution, I think. Mega Y, he stays flying and Fire type. And people who don't care anything about Pokemon are just asking us to stop at this point. So instead, we'll talk about what the rest of the class wants us to talk about. And we'll talk about magnetic flux. Does anybody have any idea? Can you give me an estimate or an idea of where I'm about to go with this based off of what we talked about in Unit 1? Let's back up. What is electric flux, right? Hopefully you haven't brain dumped this because we still have a final exam coming up in like 6 or 7 weeks. So what is electric flux? Okay, so what William is saying, I think, is on the right track. the idea of flux is how much of something passes through something else, right? So we defined electric flux as being how much magnetic or electric field passes through, say, the surface of my tablet or something along those lines, just assuming my tablet was two-dimensional. And then we said, okay, if it was a three-dimensional object that has an inside and an outside, needing a closed surface, then there was flux associated with that closed surface, and according to Gauss's law, how much flux comes in or out of my water bottle is determined by how much charge is inside my water bottle, right? So where we're going with this is magnetic flux, well, is a measure of how much magnetic field passes through some surface. That's all it is. So if you want to measure the magnetic flux, as we similarly defined it to electric flux, magnetic flux is how much magnetic field dotted into the normal vector of a surface times the differential area, and then you integrate over that region. For a constant magnetic field and a surface that has no curves to it, meaning the normal vector is not changing the direction, it ends up being that magnetic flux, just like electric flux, is going to be BA cosine theta. Magnetic field strength times area times the angle between the magnetic field and the normal vector. And it turns out that this has my all-time favorite unit in physics, at least at the intro physics level. The measure of magnetic flux is measured in Weber. Weber, which are Tesla meters squared. Do what? Because a guy named Weber is the first person to define this. His last name. His parents were not so mean to name him first name Weber. Imagine. My middle name is Vester. My dad and my grandfather's middle name is Vester, but my grandfather is the only one who went by Vester. And I told my wife that I really wanted to name our son Vester something Waldron, just like my grandfather. She was like, he would get made fun of so much in school. So instead, he's Isaiah Vester, so he just follows the middle name, just like the rest of us do. Magnetic flux. A Weber is a measure of magnetic flux. How much magnetic field goes through some area? So if I have a hula hoop out here in the classroom and I measure how much magnetic field strength, or I integrate the magnetic field strength that goes through that hoop, then that would be my flux measured in Weber. So a Weber is a huge amount of magnetic flux, right? That would be 1 Tesla over 1 square meter, and 1 Tesla is a very strong field. So Weber, just like everything else we've talked about so far, is probably going to be measured in the milli, micro, nano scale, and make sure you're comfortable with those. For a uniform magnetic field, this is what I said on the previous slide. For a uniform magnetic field that passes through a surface that maintains a constant angle, meaning that the surface has no curve to it, the previous equation simplifies, and what we will use most often in this class is phi sub m, the magnetic flux, is equal to the National Basketball Association times the cosine of theta. Is that what NBA stands for? I don't actually know. National Basketball Association. Okay. A lot of offense, no defense. That's all I know. I don't know. Not a fan of the NBA, or is that a wrong assessment? There's defense? Okay. All of my friends who prefer college basketball would argue otherwise, that they feel like it's just taking shots and going for it. But like I've told you many times before, I know nothing of sports. I'm just parroting what I've heard my friends say and argue about. I'm a physics major. I walk away from sports conversations. What's up? B is magnetic field strength. N is the number of turns in the loop. A is the area of the loop. And theta is the angle between the normal vector and the magnetic field strength, or the magnetic field. Say that one more time. No, it could be for any type of current loop, right? Instead of a solenoid, what if instead if I've got some sort of hula hoop, if I wrap a wire around it 10 times, something like that. It's just a convenient way to, if you imagine that solenoid was really compact, then then these assumptions would be true. The magnetic field is constant inside of there, and the area that it's passing through is going to maintain a constant angle, and so it's going to have so many loops. So the solenoid is just the classic. This is assuming a constant external magnetic field, not the magnetic field of the solenoid. However, if you saw my announcement about the lecture videos and you've already watched both of them, you can kind of see where we're going with this, right? Because we're getting to a discussion on magnetic induction. Like we're trying to induce currents and other things. We're getting to transformers, right? So if we have a transformer, you've got one coil that can generate a magnetic field, and it induces a change in magnetic flux in a different coil. But the problem is, and William's on the right track here, is you can have what's called self-induction. And so you have a solenoid that is isolated in space, and you set up a magnetic field inside of it due to the current inside of the solenoid. It's going to resist changes in the current because you're changing the magnetic field that comes from the solenoid inside the solenoid, and so it's going to resist that change. So solenoids are called inductors. They act in terms of, if you look at the equations of motion for current inside of a circuit, an inductor acts like a momentum factor. The more inductive materials that you have, the harder it is for you to change the current. Just like if you have something that has very low mass, it's very easy to change its velocity. If you have something that's very high mass, it's very difficult to change its velocity. So inductors act more or less the same way, but we're getting ahead of ourselves. Faraday found that when magnetic flux changes through a current loop, there is an induced EMF given by Faraday's law, and that induced EMF is minus d phi dt. That is, the induced EMF opposes the change in magnetic flux, and this is specifically this opposition here, this opposed to change. The mathematic relationship is attributed to Faraday here. The negative sign, meaning the oppose of change, is attributed to Lenz's law. It always opposes the change. Yes, that negative is very important. In fact, my graduate E&M instructor here at UAH said this is the most important negative sign in all of physics. And he was quoting some other, I don't remember which famous physicist, like Feynman or something like that. But this is the most important negative sign in all of physics, because without this being negative, EM waves and the interrelationship between magnetic and electric, all of it would break down. Andrew? Okay, so his question was, what specifically are you trying to do to cause that change? There are 3 easy ways to cause a change in magnetic flux. You increase or decrease the external magnetic field strength. Well, if you've got a loop here, right, and I increase how much magnetic field strength is going into the loop from somewhere else in the universe, changing the magnetic field strength changes the flux. Another thing you can do is you can change the area. if you have some sort of mechanism that can allow your area to grow or shrink, that will increase or decrease the flux. The other is change the orientation. If you change the orientation, you have to deal with that cosine theta term. Changing the orientation, if the magnetic field is coming from you towards me, and I've got my loop like so, and then I turn it this way, I go from some flux to no flux. So I can change the magnetic field strength, I can change the area of my loop, or I can change the orientation of my loop. All three are going to give me a change in flux. All three are going to cause an induced EMF in my system. So the most common way you think about it is you can generate AC power this way, right? You've got some way to create a magnetic field, and then you create some sort of driving mechanism to turn a motor that has a current loop. And as you continually turn that current loop, it is going from magnetic flux going in one direction to zero to magnetic flux going in the other side to zero, and that process continues indefinitely until you turn the motor off. And so what you end up getting is an oscillating, an alternating current, an alternating EMF inside of your current loop. So we're getting to the idea of generators giving us AC power. So what this is showing is the idea of Lenz's law. I'll come back to your question in a second. Maybe this will give you, answer your question a little bit. So I've got a bar magnet, and let's assume that it starts where it is in the picture, and then I shove that bar magnet towards that conducting loop. What happens, according to Lenz's law, is there is going to be an induced magnetic moment to oppose the change. So I am increasing the magnetic field as I bring in this bar magnet. I'm increasing the magnetic field strength to the right as I shove this magnet in with some velocity. And so nature seeks to oppose that change by creating a magnetic field pointed to the left. I'm increasing the strength to the right. Nature opposes it by creating a magnetic field pointed to the left. It's trying to maintain what the magnetic field was inside the loop dt seconds ago. A differentially small amount of seconds ago. Well, to do that, there has to be a current flowing through that conductive loop. And if the magnetic moment has to point to the left, you can use the right-hand rule and get that the current is having to flow around this loop in the counterclockwise direction. Well, Faraday's law said that there's induced EMF inside of this. How are we getting to the idea that there's current inside of this loop instead of just an induced EMF? What's the relationship? What? Yes, but what specifically? A very famous law that we have talked about so far in this class, relating EMF, which is voltage, to current. Ohm's law. Ohm's law states that V is equal to IR, so if there's an induced EMF and you know what the resistance of your loop is, you can tell what the current is going to be. Your question? Yes, there will be an induced EMF that will cause the current. Again, if it's this right here and I end up pulling somehow I pull that conducting loop apart where it's larger, the magnetic field strength is coming from you towards me, so it's pointed in this direction. I have increased how much flux is coming towards me. It's going to induce a magnetic moment going towards you, and to do so, it would have to have a current going in this direction around that loop as I spread it out.
So with
The strength of the current would have to be proportional to the rate of growth of my loop. Right? If I increase my area very, very, very slowly, I'm increasing the flux very slowly, so d phi dt is very small. There's a small change over the time, but if I do that very rapidly, I would get a big jump in the current. You can see this. I don't know exactly what they have you do in the lab, but one of the things we would have our Harding students do is you do this right here, and qualitatively take the magnet and shove it in very slowly to a current loop. So there's a very small change with respect to time, and you get a very small blip in the current inside of the loop. Or instead, if you do it with some medium pace, you get a much sharper blip on the current. And then as you shove it in very quickly, you get a very sharp peak in terms of the induced EMF, the induced current inside of the loop. Another way you could think about this, since velocities are relative anyway, is what if the bar magnet stayed still, but now I'm moving the current loop away from the bar magnet? Well, now you see that the induced magnetic moment is in the opposite direction as the previous slide. It's now pointed to the right in the same direction as the magnetic field from the bar magnet. So what's happening here is when the ring is where it is right now, it has a certain amount of magnetic field strength pointed to the right. And as I move the ring away from it, I decrease how much magnetic field strength I have pointed to the right. This is the most common mistake when students solve problems with Lenz's law. Most students assume that the induced magnetic moment always points opposite to the magnetic field, which is not true. It points opposite to the change in magnetic field. The change in magnetic field, I get a decrease in magnetic field strength to the right, so I get a magnetic moment that is induced in the same direction, in the sense that it's trying to maintain the magnetic field that is pointed to the right. Another way to think about it, if I go back to my slides here, when the ring is, let's say, 2 centimeters away from the magnetic field strength, my B initial looks like so, and as the loop moves away, say 10 centimeters, B final is going to look something like this. And so if you want delta B, which is B final minus B initial, so that's going to be, let's see, B final looks something like this, minus B initial, so it's going to point like so. That means delta B points like so, to the left. But on the previous slide, it had the induced magnetic moment pointed to the right, not to the left. I just found that it was to the left here. So what am I missing? What am I forgetting? What's wrong? Did I make a mistake? No, I didn't make a mistake. Everything is correct so far, but we said that the induced EMF, therefore the induced magnetic moment, goes as minus d phi dt. The area of my loop is not changing. The magnetic field strength is what's changing. The area is not changing. Orientation is not changing. So I could think of this as minus delta B over delta T times A cosine theta. So I have to consider that there's a negative delta B. So negative delta B would be to the right. So I get an induced magnetic moment when I decrease the magnetic field strength in a particular direction. The magnetic moment points in the same direction as the external magnetic field. Lenz's law says the induced magnetic moment opposes the change in magnetic field strength, not the field itself. So another way to think about this is I've got an iron rod to act as a conduit for the magnetic field, and I turn on the switch here, allowing current to flow through this first solenoid here, in which case B would start increasing to the right, which is going to create a magnetic field in the second solenoid to the left. And then I can turn off the switch, which means that the magnetic field is going to suddenly decrease in the first solenoid, and I get a magnetic field that is induced to the right to maintain the decreasing magnetic field strength. I want to say here, let me pull this up. I feel like, there's a PhET electromagnetic lab. It would be worth your time here to pull up the PhET magnetic lab, and so you can have here you go. You can end up getting, if I just leave the magnet inside of the loop here, nothing happens to the light. But if I change the magnetic field inside of it, then I can change the strength of the light. If I do this very slowly, then I get that the light shines very dimly. Or if I do it very quickly, I get a very quick burst of bright light. You could also do it in terms of voltage, and you could see it here as you go in and then out. There's going to be a change in the voltage across this resistor right here. Or we could instead, just like Andrew and I were talking about, if you have the bar magnet look like so, you can change the area, and you'll notice on the voltage meter, I get a very small change in the induced voltage, the induced current, as I change the direction here, or as I change the size. I'm trying to think if there's anything else, but I would encourage you to play with this a little bit and try to get a feel for what's going on with electromagnetism. You can even work with transformers. You'll notice that for DC power, in my first conducting coil, I get no induced current in my second conducting coil. But if I switch to AC current, then what happens is I get the light shining very dimly. You can increase the field strength and the light's going to shine brighter, or you can make the change happen very quickly. And now you see exactly what happens if you put a slow motion or a high frame rate camera in this classroom. That the lights in this classroom are actually going to flicker on and off at 60 hertz, 60 times a second. Because the AC power that we use functions at 60 hertz. You can see this noise everywhere if you use an oscilloscope anywhere in a lab. You'll pick up the 60, 120 hertz signal anywhere you are in the lab, because the wall is always going to give you noise at the same frequency that we drive our power grid at. Play around with this if this lecture on Lenz's law and Faraday's law has been utterly confusing to you. The more that you play around with it, the more you'll gain some intuition about it. Until then, I will see you on Thursday. Y'all have a great day.